So I will be giving you an introduction to the Techila system on a very high level. So I will be telling you how it works and what sort of problems it can solve and what types of problems are not that well suited for the computation in Techila. And I will also show some practical demos and instructions on how to configure MATLAB installation to work with our Techila SDK so that you can push computational workload through the Techila environment in CSC. And of course, if you have any questions, we can also answer those after this webinar. And to start things off, I will show you a demo on how the Techila system can be used to speed up MATLAB computations. And you should see my screen now where I have a MATLAB session running. And this is the demo code that I will show you. And on this computer, I also have the Techila software development kit installed, which allows me to push the computational workload to the demo Techila environment I'm using. And this is a quite long M file, as you can see from the size of the scroll bar, but there are just a couple of important parts we want to focus for now. I'm just going to scroll down to the interesting part. So these are just the parameters that are set for the computation. And then we get to the part that will do the Techila distribution. And you see these Cloud Core and Cloud End keywords here. These Cloud Core and Cloud Ends are actually functions that are included in our Techila software development kit's MATLAB toolbox. And this Cloud Core function will allow us to execute iterations in this for loop structure in a Techila environment instead of on a local computer. So just to illustrate my point, if I would remove the Cloud End tags like so, and Cloud Core tags like so, it converts this to a locally executable version. So now, if I would run this code, it would run locally on this computer without using any Techila components. But now, when I replace the for loops with Cloud Core loops, like so, and ends with matching Cloud Ends, it marks the code block within the innermost Cloud Core loop for execution in the Techila environment. And in this case, we are minimizing our function and we are storing the result in a matrix at the indexes specified by the IDXY and IDXX variables. So when I run the code, it will generate a two-dimensional matrix with a size of 150 times 150, if I remember correctly. And these CF notations here are additional control parameters for the Cloud Core syntax. And in this case, these are used to execute the fallback functions on this computer to visualize the data. So whenever we get new computational data from Techila environment, we will refresh a 3D graph to show the computational results. And now I'm just going to run the code and I'm going to change the directory that contains it. And now it started processing it. And a lot of stuff happened when I ran the code. And I'm just going to go through what happened, or the most relevant parts of it anyway. So first we get a message saying that the Techila initialized. And this means that the Techila SDK was able to successfully establish a network connection from this computer to the Techila server. And it means that I am able to use the computational environment. And after that, we got a lot of text messages, but let's instead focus on the project status window you see here. So the green indicates jobs that are completed, yellow indicates jobs that are running, and gray indicates jobs that are still waiting for computational capacity to become available. And on the right here, you see the graph I mentioned before. So it's a 3D graph that's being used to visualize the computational data that's being received from the Techila environment. So every time a new computational task is completed, the result will be automatically transferred back to this computer, and the data will be visualized in the 3D graph you see here. So each of these squares is actually a computational task, or the result of a computational task. And now, because I forgot the semicolon, I think we still had enough scroll room. So I got basically printed the result I got from the Techila environment. So it printed a 150 times 150 array, which was the data that was visualized in the graph. But the reason why I scrolled up is because I want to show you the project statistics info that's shown each time you complete a computational project in a Techila environment. And I'll just go through some of the key points in this statistics printout. So the project ID number is just a unique identifier for the projects that are executed in a Techila environment. And it's just a running counter from 1, and it increases by 1 every time a new project is computed. So if I would run the code again, it would create a new project, and it would have the project ID number 246. And in the demo environment I used, it had 20 Techila workers, and that's the reason I also have the value 20 here. So it processed the computational problem on 20 different computational nodes. And then we have some information about the total CPU time used to compute the project and the amount of wall clock time used to solve it. And in this case, we were able to do about 1 hour, 10 minutes of computation in just over 1 minute. So if we, to simplify it a bit, if I would run this on a computer with similar hardware specifications as the one I'm using in the demo environment, it would take roughly 1 hour to complete. 1 hour, 10 minutes includes some data transfer overhead and initialization overhead, so it's actually a bit longer than it would take to run the code sequentially on one computer with the MATLAB running. But it's a good approximation value about the amount of computational workload done. So 1 hour of computation done in 1 minute, which gives us an acceleration factor of 62. So it's just this acceleration factor is calculated by dividing these two values. So 1 hour 10 minutes divided by 1 minute 8 seconds is this value. And then we get some information about the jobs. So when I ran the project, it created one project, and this project consisted of, let's scroll up a bit, of 169 jobs. And this job statistics window gives you an idea on what the properties of the computational jobs was. And the first one gives you an average CPU core usage, which in this case was 96.99%. And this is calculated by the amount of CPU time the job used divided by the wall clock time. And this 96% is a good value, and it means that the computational job was sufficiently large and it didn't have any data transfer bottlenecks or anything like that. And it means that the job was able to use the CPU core efficiently. In some cases, if you are, for example, processing workloads that are consisting of extremely short jobs, then this value will be typically lower because the relative amount of overhead per job is higher, which reduces the efficiency. And then we get some information about the average CPU time used per job and the minimum and maximum values, and then also some information about the memory usage of a job. So in this case, it used 200 megabytes per job, which is a quite small value. So we are not dealing with anything memory intensive in this case. And this code also had a locally executable tick tock, which measured the time from start to end. And if we compare this value, 1 minute 17 seconds, with the wall clock time used here, 1 minute 8 seconds, we see that we have some data transfer overhead, which was caused by the data that's transferred from this computer to the Techila environment, and also receiving the result from the Techila environment to this computer. So that took 9 seconds in this case. And this, of course, will vary depending on what type of computational application you're running. If you have large data amounts that you are transferring to the Techila environment, you will have larger overhead because the amount of data transfer will be bigger, which will require more time. So that was the demo, which I wanted to run at the start, just to give you an idea on what using Techila with MATLAB actually means. So because I had Techila SDK installed on this computer, I was able to use the Cloud Core functions, which are included in Techila SDK, and the Cloud Core functions enabled me to execute the iterations in this computation-intensive for loop structure in the Techila environment instead of on this computer. So that was the demo, and now I have some PowerPoint slides I'd like to go through just to give you an idea on the general properties of the Techila system. And if you have any questions at any point, just feel free to write them down to the chat, and we can cover those at some point later during the webinar, because I will probably miss them while I'm talking. Okay, so how Techila speeds up computations? And Techila does this by dividing the computation problems into independent smaller parts which are solved simultaneously in the Techila environment by using typically a very large amount of CPUs which have a lot of cores. So we are not just using one very heavy server which has 20 or 30 or 50 CPU cores. We are using several dozens or hundreds or thousands of different computers which all contribute to solving the computational problem, which has been divided into independent parts which can be executed on these workers. And then, just to give you some idea on what types of applications can be sped up, I have listed some of the most typical use cases Techila is used with. And the first one I'd like to mention is Monte Carlo type simulations that rely heavily on random number generation or random number sampling to solve a computational problem. And these are typically such that they consist of independent iterations, meaning that they can be divided into independent parts and executed simultaneously on several different workers, which can reduce the amount of computing time required to solve the computational problem dramatically. And another typical use case is a situation where an end user has, for example, 100 video or audio files, and they want to analyze all of those files using the same application. This is another very well-suited application to be running Techila, because we are able to send these data files to Techila environments so that each worker gets a separate data file, and then it can execute the algorithm that you want and analyze the file, and it can generate output data, which you can then receive back to your computer. And then, of course, whenever you have a use case where you want to execute the same application but with different parameters, Techila can be used in these as well. But if your computational problem consists of some structures that are very strictly recursive or have recursive dependencies, for example, MC-MC chains, then these types of applications are not that well suited for Techila because of these dependencies. So we are not able to divide it into independent parts due to the dependencies. And then I have an illustration on what happens when an end user uses the Techila environment to process computational workload. So this is the same situation when I ran the demo, and now I just have a small animation that explains what happened during that project. So at the start, the end user needs the Techila SDK. And with this SDK, they are able to establish a network connection to the Techila server. And this connection is secured using SSL, and it is authenticated by using their own personal Techila user credentials, which they can ask from their Techila admin. And after establishing the SSL connection to the Techila server, the end user will have access to all of the Techila workers that are available in the computing environment. And these connections between the Techila server and Techila workers are also secured using SSL. And after establishing the connection to the Techila server, the end user is able to send the data to the Techila environment. And this all happens automatically. So you don't need to manually send the data or drag any files to anywhere. It's all done automatically. So when I ran the computational demo project earlier, it sent data from that computer to the Techila environment. I didn't need to type in any manual commands. It was all done automatically. But the key point is that the data is sent to the Techila server, which acts as a communication endpoint between the Techila environment and your computer. So whenever you want to use the Techila environment, all the data is sent through the Techila server. And the Techila server will then distribute the data and the computational tasks to the Techila workers. And Techila workers will then process these computational tasks, which will generate some result data, which is illustrated by the blue balloons. And this result data will be then automatically transferred back to the Techila server, which will transfer it back to your computer. So this means that you are able to push the computational workload from your MATLAB session, and you are able to get the result straight back into your MATLAB session as workspace variables, essentially. And here I wrote down some of the typical languages this Techila SDK is used with. So in this webinar, we are focusing on MATLAB, but we also have support for R, Python, and a variety of other programming languages as well. Then I have some information about the Techila setup in Taito. So currently, which is in this case yesterday, there were 42 Taito nodes that can be used for processing Techila jobs. And each of these nodes can process 12 jobs at the same time, meaning that the system is able to process 504 jobs in total. So 504 individual computational tasks can be processed at any given time, assuming that all the capacity is available. And currently, there is no CPU core limit per user. So if you are the only user in the Techila environment, you will get access to all of the capacity. But if the system is crowded and it has multiple end users using it at the same time, the system will automatically share the computational capacity between all users, and it tries to divide the computational capacity evenly, meaning that if an end user has gotten previously a very large amount of CPU time and a new user comes online, the new user will get a slight bump in the priority, meaning that they will get a little bit more of CPU time at the start to even things out. And now, if you want to get Techila access to the CSC environment, CSC has written a nice guide at the link you see here. So there are instructions and a getting started section at the address you see there. And if you go to that link, there are instructions which include also the requesting the end user key, which is essentially your own personal end user credential package. And this page also contains a link which you can use to download the Techila SDK, which is required in order to access the Techila environment. So this Techila SDK contains all of our library functions, including the MATLAB's cloud core statement, which I used during the demo. And the Techila SDK, just to repeat myself, which was the component that is installed on your computer, contains lots of documents for getting started with Techila. And for MATLAB users, we have a document called Techila with MATLAB, in this software development kit, which contains helpful information about the features available in MATLAB and also some walkthroughs of the example material that's included in the Techila SDK. And in the Techila SDK, I already mentioned that we have the Cloud for Helper function, and I'd just like to go through that a bit more in detail. So here we have a very small screen capture of a code implementation that uses Cloud for. And Cloud for is used to distribute computational intelligent for loop structures. And on the left, you see an M file or a screen capture of an M file, which contains the main function, which in turn contains this Cloud for loop. So whenever the Cloud for is used, it needs to be matched with a matching cloud end. And in this case, the Cloud for and the matching cloud end only contain this one line of code, meaning that this line of code will be executed in the Techila environment. But it can be much more complex. So in the demo, for example, I had several lines of code there. You can have pretty much anything there that you want to execute in the Techila environment, as long as it consists of independent parts that can be solved simultaneously. And of course, you want to focus on the computationally intensive for loop structures due to the overheads that are always present when you're doing distributed computing. So if you use Cloud for in a very computationally trivial loop, the performance will most likely be worse than it would be when executed locally. But in this case, I'll just go through what this would do. So if I would execute the main function, it would set the value of loop to 100, and then it would mean that the Cloud for would iterate from 1 to 100 and execute this comp func with the different input arguments during each iteration. And the results would be stored in this result variable at the index specified by the loop counter. So as the result, I would get a vector of which would have 100 elements of double values in this case. And this comp func can be defined in the same M file as it's done here, or it can be located in a different M file in, for example, the same directory or other directories on the MATLAB path. And then, just as an addition to the previous slide, Cloud for can also be used in a nested situation. So in this case, we have a single Cloud for loop because we only have a single for loop in the local version. But the example here has two nested for loops in the local version, and the results are stored in a k by j array at the indexes specified by the loop counters. And in this case, because Cloud for can also be used in a nested fashion, we're able to replace both for loops with Cloud fors and of course this matching cloud ends. And if I would run this code, it would generate a k by j result array, which would contain the same values as the local version. And then some words about the default behavior of MATLAB, and just some things to bear in mind. So whenever you use Cloud for in your code, all workspace variables that are defined when the Cloud for keyword is encountered will be transferred to the Techila environment. So this is the default behavior. And by default, this works very nice because it transfers all the variables, meaning that any variables that you would use during the for loops are available. But in some situations, for example, if you have very large arrays that you are using, for example, to store the data, but you don't need those for computation, it doesn't make sense to transfer those to the Techila environment. And in those types of cases, you can use the Cloud for control parameters to specify a list of workspace variables that you want to send to the Techila environment. So you can essentially define a comma-separated list of variables that you want to send. So this can be useful in situations where you have lots of workspace variable data, but you don't need all of those during the computers. And whenever you are using Cloud Core, Cloud Core automatically performs an estimation on how long one iteration takes. So let's say that you would have a Cloud Core loop that consisted of 1,000 iterations, but you would do something extremely trivial in each iteration. For example, you just multiply the value of the index counter by 2 or something like that. Then, because of this local estimation, the iterations will be grouped so that multiple iterations will be performed in each job. Because in that type of situation, it wouldn't make sense to create a project consisting of 1,000 jobs, and each of those jobs would just execute one iteration, which would multiply the value of the iteration counter by 2. But instead, it makes more sense to group the iterations together so that we process all of the iterations in one job, or for example, half of the iterations in 2 jobs. So this is a safety mechanism to prevent extremely short jobs in situations, for example, where you have a Cloud Core loop which has 1 million iterations, but the iterations themselves are not that long. In this case, Cloud Core automatically groups the iterations so that each job performs multiple iterations instead of one. And then we have some words about I also talked about the control parameters that can be used to fine-tune the performance. And here you can see an example of the syntax that's used to define those. So it starts with a % mark, followed by Cloud Core, and then in parentheses we have the control parameter and the value for that parameter. So this is, it looks like a MATLAB comment because it starts with a % mark, but Cloud Core recognizes this %Cloud Core keyword and interprets the control parameter and its value, and will use it to control the computations in the desired manner specified by the parameters. So that was Cloud Core, and then we also have a second helper function in our SDK, which is called PEATS. And PEATS is the fruit, but it's also an acronym from parallel each. And this can be used to execute computationally intensive functions with different parameters, so for essentially performing parameters without computations. And here we see another screenshot of some M files. So here we have a main.m, which contains the teach function, which will define what we want to execute in the Techila environment. And in this case, the parameters for teach start from this parenthesis and end here. And this syntax would specify that we want to execute a function called compfunc, which would be this function here. So we would execute this function in each job, and we would give one input argument to the function. And this param notation you see here is a special notation in Techila, which will be automatically replaced by values of the teach vector you see here. So in this case, the teach vector will range from 1 to 100, meaning that there will be 100 jobs, and the value of this notation will be different in each job. So job 1 would execute compfunc with input argument 1, job 2 would execute compfunc with input argument 2, and so forth. And when using teach, the result will be returned into the defined return variable in a cell array. So in this case, because we have 100 jobs, the cell array would consist of 100 cell elements, each containing the result generated in one job. And here I have another example of the teach syntax and what are the minimum parameters that need to be defined. So at minimum, you want to define what you want to execute in the Techila environment, and that's done by using this first parameter for the teach function. And then the second parameter is used to define input arguments for this executable function, so this, in this case, worker function. And the input arguments are defined using these curly brackets and are separated by commas. And in this case, we have two input arguments here, meaning that the worker function should be a function that accepts 2 input arguments. And the value of the first input argument will be the same in each job. So it will be the same because we have defined it statically here. So we set the value to 5, meaning that the value of the first input argument will be 5 in each job. But the value of the second param notation, which was the special notation used for parameter sweep type computation, will be different in each job, and in this case will range from 1 to 10. And then we have the third parameter, which is an optional parameter. And when defined, you can use this parameter to define a list of data files that you want to transfer from your computer to the Techila environment. And any data file that's transferred using this syntax will be copied to the same temporary execution directory with the binary containing the executable function. So you don't need to worry about what folder contains the data files on the worker. They are all patterned and they will be stored in the same directory. So that was pretty much my PowerPoint slides. And now I'm going to go over the steps that you need to do in order to configure the Techila SDK on a computer. So here we have a Linux computer, and I have downloaded the Techila SDK to this computer previously. And Techila SDK is delivered in a Techila SDK.zip file. And the first step you need to do is to extract it. And when you extract it, you will get a folder called Techila, which is the root directory of the Techila SDK. And in the Techila SDK, you will have a file named Techila settings.ini.template. And in that file, actually we don't want to open that file yet, so let's close it first. So this is the Techila SDK configuration file, and it contains the network address of the Techila server and the location of your own Techila key store. And the first thing we need to do is to remove the .template suffix of the file. And after you remove the .template suffix, the name should be Techila_settings.ini. And then you want to open it with a text editor and change a couple of lines in the file. And the first line you want to change is the parameter hostname. And the hostname parameter defines the network location of the Techila server. And this IP is the demo server I'm using, but in your case, you would want to specify the value shown here. So this is the network address of the Techila server, so techilasrv.csc.fi. So you want to enter that value there. And another value you want to use or specify is this key store parameter. So this key store parameter is used to define the location of your personal key store file. So your personal key store file, you can get it by requesting user credentials according to the instructions in the web link I showed earlier. And then the CSC admin guys will send you a key store, which is password protected, and it will be probably named something like yourname.jks. And in this case, I am using a file called demokey.jks. And in this case, I have used this macro, which is in curly braces, this inidir. And this is very handy because it will be automatically replaced by this path. So the path that contains this file will be automatically replaced here. But you could, of course, have the value configured here. So just for example, say key store my name. This would work as well. But you can also use this inidir macro as long as you store the demokey.jks file in the same directory, you have this ini file. So as long as you have these two files in the same directory, you can use the inidir macro notation and it should work just fine. Just going to replace that. So I'm going to save. So that's the first thing. You want to remove the .template suffix, so its name will be techila_settings.ini, and then you want to edit two values in that ini file, and the first value is this key store parameter, and the first value was this hostname parameter. Anything else you can leave at the default value. At the default values, you don't need to edit those. And then you can start up your MATLAB. Clear the printouts. And then in MATLAB we need to do a couple of things. And the first thing we want to do is to change our current working directory into the Techila SDK's root directory. And then we see this lib directory, which contains all of our library functions, so we go there. And then we have this MATLAB directory, and we will also go there. So now our current working directory is Techila lib MATLAB. And this contains our MATLAB, a small MATLAB toolbox. And we want to update the MATLAB search path to contain this directory so that we are able to use the Cloud4 functions and other helper functions included there as well. So we can do it by executing this install SDK command. But you can also, of course, use any other tools for this, for example, path tool or add path or whatever you prefer. The key point is that we want to add this directory to the MATLAB search path. And after that, we want to configure the MATLAB compiler. And the MATLAB compiler is needed to compile the code into binary format, which can be then sent to the Techila environment for execution. And the MATLAB compiler is configured by using mbuild-setup. And you should get, in this case, the compiler GCC is installed on this computer, and that means that it will print out the message for this compiler. If you're using some other compiler, you might get a different message. Now we have updated the MATLAB path, and we have also configured the compiler. And now we can test the connection to the Techila environment. And we can do this by running a simple command called Techila init, which will create a test session using the Techila SDK and your personal user credentials to the Techila server. So this will test network credentials and the key store credentials. And apparently I mixed up some values. Let's do some online troubleshooting. So let's open this editor. Yeah, okay. But this gave us a good idea to on what happens if something is wrong with the setup. So in this case, we had an error saying that the certificate is unknown. And in this case, the reason is on this line, essentially. I commented out the wrong lines because I'm using this demo environment and not the CSC environment. This is a bit specific because you typically don't have several Techila environments that you're connecting to. But anyway, if you are using a wrong certificate or a certificate that is not valid, you will get an error message like that. But now let's just save it. So I saved the file, but before that I made this line uncommented. Now we can try it again. And now it works. And this is the expected output if everything goes okay. So this tested the network connection and the Techila credentials. And after that, you're ready to run your first project. And you can use the Techila SDK's example material to do these first computational test projects. And I'll just change the working directory here to the Techila root directory. And I'll actually go through what the Techila SDK contains while we're here. So the temp directory will be created automatically in this directory, and it will contain all the temporary files created during project creation. The logs directory will contain all the log files that are generated whenever you run projects. So if you run a project and you get errors, these errors will be stored in these log files. The lib directory contains all of our library functions, and for MATLAB, it contains the small MATLAB toolbox, which includes the CloudCode helper function and the Teach helper function. Then we have this doc folder, which contains a lot of PDFs. And as we are talking about MATLAB, this document is probably the most relevant for you. So the Techila with MATLAB document contains walkthroughs of all of the example materials and also the commands needed to configure the Techila SDK. So the install SDK and build setup can be also found there. And then we also have this. So this demo folder is something that I just created. So you don't have this in the standard SDK. But the examples directory will probably be very useful for you when you're starting to use the Techila system. So the first level of directories is divided based on the programming language the example covers. So for MATLAB, we want to go to MATLAB. And then we have several additional folders. And the folder for Cloud for examples is this one. So we have several very simple Cloud for examples and some more advanced ones that show you how you can use the Cloud for helper functions to push computational workload to the Techila environment. Then the tutorial and feature folder contain the Techila SDK's example material for Teach, so parallel each. And when you're starting to use the system, it's probably a good idea to start with the simplest example in the Techila SDK, because we first want to verify that everything works. I have run this example earlier, so we have some additional data files. I'll just remove that one. So our current working directory is the directory that contains the example files, and then we want to run this file that starts with run underscore. So whenever you have a file that starts with run underscore, that means that that file contains the Techila enabled version of the code. And whenever you see a file that starts with local underscore, it means that the function is executed locally and will not do anything in a Techila environment. So this is basically a reference implementation that you can use to compare the changes needed when changing from a local implementation to a Techila implementation. Now we're interested in this one. So this is a very trivial example. There are more comments than code, but let's go down to the important part. Well, first it takes one input argument, jobs, which will be used to set the length of the speech vector. So it will be used in the speech function call, which will define that we want to execute a function called distribution dist, which is located in the same directory. We don't want to give any input arguments to the function, meaning that we are using these empty curly brackets, and we want to create a project consisting of a certain number of jobs. So if we set jobs to 10, it would create 10 jobs. Let's run it, and you can see what it looks like. And now we got the message saying that Techila is initialized, and this means that the network connection and my user credentials work with the Techila environment. Then we get this compiling distribution dist for Linux AMD64 locally, and this means that it's compiling the function in this file into a binary format, which can be sent to the Techila environment for execution. And depending on the complexity of the code and the CPU you're using, the compilation will probably take something 30 seconds to a minute or so. But this compilation only takes place in situations where an existing compilation doesn't exist. So now, because I ran the code for the first time, it needed to compile it into an executable format that could be sent to the Techila environment for execution. And let's do some, okay, we got the project ready, and it took well, quite a long time, but the reason for biggest delay in that one was the compilation. But just to illustrate my point, I'm going to run the code again, and this time it should be much quicker. So it didn't do the compilation, and the reason it didn't do the compilation is that the code didn't change. And when you don't change the code, you don't need to recompile it, because we have an existing compilation that we can use. But if we do some modifications to the code, for example, here, times 10. So this was a change in the executable code. And now when we run the code, the Techila SDK detects the modification and it will need to recompile. But this is a very simple example and doesn't illustrate all of the points I'd like to explain at this point. I think we next will show you how you can pass input arguments to the executable code using this beats function. Then we can go through a couple of Cloud Code examples, just so you can see what the example material for those look like as well. While we're waiting for that, I'll actually quickly show you the with MATLAB document so you can have an idea on what that looks like as well. So this is the Techila with MATLAB, and as you can see, it's quite lengthy. It's 114 pages, and the majority of this document consists of walkthroughs of the example material. So let's just go to this one. So this is a walkthrough of the first example that I'm running now, and it walks you through on what happens when you run the code and how the parameters of the pitch function affect the code that is executed on the Techila workers. And in this case, we are not doing anything trivial. We're just summing the values 1 plus 1. And this is a situation where you typically wouldn't want to use Techila because this is very computational trivial. But this is in the Techila SDK as an example, simply because it provides a very simple reference point that you can use to see what is actually being executed in Techila. There are also lots of other more advanced example materials in Techila SDK. But that was the first example. Then I'm going to show you how to pass input arguments to the executable code by using the pitch function. So this is another tutorial example. And then we again open the run underscore file to see the pitch code. And then we open the underscore dist file to see the code that will be executed in the Techila environment. So here we have the local control code, or the code that's executed on this computer. And it takes two input arguments, multip and jobs. And by the highlight, we see that multip is used here, meaning that it will be passed as an input argument to the code that will be executed on the Techila workers. So the value of multip will be given to this function as the first input argument in each job. And the second input argument is this param notation, which is used to do the parameter sweep computation. And this will be replaced with values from 1 to the number of jobs in each job. So just going to define value 2 and 5 jobs. And let's see what this parameters list looks like. So when I execute the local control code with these parameters, the value 2 will be set here as well. So this will be the same in each job. And the second parameter was this param notation. And it will be replaced by 1 in the first job, 2 in the second job, and so forth. And they will be just multiplied, these values. So when I run the code should generate a project consisting of 5 jobs. And the first job should multiply values 2 and 1. Job 2 should multiply values 2 and 2. Job 3 would multiply values 2 and 3, and so forth. And then the code returns the result as the result variable, which will be returned by the feeds function. So as a result of this project, I should get a result array consisting of 5 cell elements. And in this code, because we only have double values in those result cell array variables, we can convert them to basic matrices using this cell to map notation. But if you are returning some other more complex stuff from the computational code, then of course you wouldn't. Okay, and we got the results. So as expected, we got the values 2, 4, 6, 8, and 10. So this was the feeds tutorial example on how to pass input arguments to the executable code. And let's just go through MATLAB output example while we are at it. So again, I'm going to open this run_loops dist. And I'll scroll down to the output code. And it's very simple. It's just consisting of this one line, essentially. And then we also have this one output control parameter here. And actually, I'm just going to run the code so you can see what happens. So I set the value of the input argument to 10, which will mean that the Cloud4 will loop from values 1 to 10. But as you see, it only created 5 jobs. So even though we did 10 iterations, we only had 5 jobs. And that's because we had this control parameter, which is defined here. So present Cloud4 looks like a MATLAB comment, but is actually a control parameter for Cloud4. Then we define the parameter that we want to use. So in this case, we want to use steps per job, and we want to set the value to 2. And this parameter defines how many iterations we perform in each job. And now I change the value to 5. I'm going to run the code again. And it created 2 jobs. So now it's doing all the same computation, it's just grouped slightly differently. So the iterations from 1 to 5 were performed in job 1, and iterations 6 to 10 were executed in the second job. And there are also other examples here about Cloud4, but they follow the same pattern. So there is a run_file that's used to create the Techila project, and then there is a local underscore m file that has the local reference execution of that. But that was essentially a quick demo on how to configure the Techila SDK in MATLAB. So just we started by removing the .template, so this, and then we have the Techila ini file, and using this ini file, we define the host name. So you would want to use this one, and then we define the key store parameter here, and then in MATLAB we updated the MATLAB search path so it contained the this folder, and then we also configured the MATLAB compiler. So that was that. And that was the demo. And here is my last slide. If you want more information, please feel free to check out our website. We also have some documentation available there, located under Technology Docs. And we also have a forum and a YouTube channel, which contain lots of useful information. And if you run into any problems when using the Techila system in CSC, the point of contact for you would be the email address you see there, so servicedesk@csc.f.